We are the engine that would be powering a Google Assistant or powering an Alexa. Okay, so we're a full speed of a machine learning / AI automation platform. And we are deployed globally, as you can see, our customer base that spans both telecommunications and insurance. Okay, so we drive conversational interfaces. So anywhere where a customer may engage using conversation, we are present there. And think of what's happening to us each and every day. As newer and newer devices emerge around us, right? A lot of these devices simply don't have keyboards. Give that a thought for a moment. Think of your smartwatches, they don't have keyboards. Think about the Google Pixel Buds or the Apple AirPods, if any of you use those. A lot of those don't have keyboards. And these set of tools are training us on how to use speech as an input. And my reckoning is that in a couple of years, the way we browse the internet is set to change forever. People will stop going to a website and clicking to get something. Right? The whole concept of clicks is going to go away. It's all going to be speech-based, simply because speech is the most frictionless means of interaction. Right? We just understand each other because we can understand and interpret speech. Moving on, this was what happened in 2017. Okay, so 2017, roughly 33 million devices shipped that had embedded speech capabilities. It's very, very significant, simply because if you look at what happened, it was about a 3-fold jump compared to just the prior year. And that number is going to go up and up exponentially as each year goes by, to a point that speech will just become the natural way you use and do things. You just won't have remote control for television. Why can't you just talk to your app or say something to your app and have the channel change? Why do you need to browse so many channels to get to what you want to do? So first and foremost, Mark, thanks for taking a shot at this and delineating what's AI versus machine learning. Because as a practitioner, it does bother me when people conflate terms, okay, between AI and machine learning. AI belongs to the discipline of computer science, okay, and you can have AI without machine learning. If you've ever played chess with a computer, chess in the 90s didn't have the concept of machine learning. Chess used brute force algorithms. It exhibited AI characteristics. It could behave like a human. It could figure out a winning strategy, optimize its winning strategy, and defeat each of us. And it didn't use machine learning. Okay? Machine learning, on the other hand, has its roots in statistics. So while Mark's company starts automating all the data science pieces, I would say, like, if you're pursuing a career in machine learning, make sure you don't compromise on learning the math, learning the statistics, because understanding data distributions, understanding what normalizing data is, all of these matter a lot if you want to be an effective machine learning developer. If you look at what happens within the machine learning world, okay, like I mentioned, artificial intelligence is a characteristic that's exhibited by certain systems. Okay, you have the spectrum of computer science to statistics exhibited by that system that exhibits artificial intelligence characteristics. Within machine learning, there are, again, a bunch of disciplines. Okay, so you can use machine learning algorithms for speech, for language, for video, for audio, for machine vision, and the list just goes on. As each day passes by, there are newer and newer inventions and discoveries made with these algorithms. Where we focus on, and where I do want to focus on tonight's discussion, is on language. Okay, within language, you have the concept of natural language processing, which is essentially what drives conversational interfaces. Within natural language processing, you have two branches again. You have a natural language understanding process, which is essentially the technology that powers your Google Home or Alexa or Siri. And you have a natural language generation process. How many of you heard a couple of years back where a novel in Japan was written by a robot? Okay, so what happened, since a lot of you didn't put your hands up, is a couple of years back there was a novel writing competition in Japan. And one of the entries was a novel titled The Day a Robot Wrote a Novel. And this was actually not a bunch of people writing a novel, it was actually a bunch of people who designed an algorithm to generate a novel. And guess what, it actually passed the first round. It didn't win the competition, but it did pass the first round, which meant that it didn't make literary mistakes. It could process and generate language. How many of you have used an app like Prisma? Or filters on your phone, depending upon which phone it is? A lot of them use generative models. For example, you have algorithms today that you can take a picture and transpose Van Gogh's style on that picture. And it generates a new picture. That's a generative algorithm. A discriminative algorithm, on the other sense, is when Facebook goes ahead and suggests you want to tag so-and-so person who's your friend. Or the fact that when you turn on your cameras, you have those boxes show up against faces, right? How does it know where a face is? That's a discriminative algorithm. And each of these branches further have generative and discriminative algorithms, okay? So within natural language processing, you have NLU and NLG. This brings upon an interesting debate. When will AI replace general intelligence? So a lot of the hype we are living right now is loss of jobs, what's going to happen to us, machines are going to become so powerful and so destructive and so on and so forth. I can tell you, being a practitioner in the space, it's not as straightforward as it looks on the outside, and neither is it as smooth, okay? And one example is right here. Can anyone tell me what's wrong? I'm going to give you a quick explanation. So here is a sentence that says, my car seats full. And what you see on the right is an output from a machine learning algorithm that's basically doing a process called as parts of speech tagging. So when we transpose speech, okay, into a form that machines can understand, parts of speech tagging is a way you actually render structure to the speech, okay? So what this sentence or this algorithm has figured out is that my is a preposition, car is a noun, seats is a noun, and for is a count. Can someone tell me what's wrong?
Ceases verb.
Spot on. You know what happened in this training, and this, by the way, is a very, very well-known linguistic tool in the machine learning world. What happened is that this model was so biased because it saw an overwhelming number of... Go ahead.
I think you want to repeat the answer that this gentleman
Nobody
gave.
understood.
Oh, sure. So seats was a verb in that context. It wasn't a noun. Okay? And something as basic as this can be... You do see that there's a lot of brittleness behind these algorithms, right? Something as basic as this can break down the NLU process, the natural language understanding process. Because if the machine learns an incorrect behavior, there's no way... Sometimes even finding these things become incredibly hard. Okay, so here is a concept of, to bring back the debate of general intelligence versus machine intelligence. The slew of branches that we saw in the previous slides, each algorithm is very, very specialized. And you cannot, for example, take an image of or a face tagging algorithm and use it in any shape or form for language. You cannot take language models and use them for, let's say, video processing. Each algorithm is very, very specific, is very purpose-built. And guess what? It takes a lot of time and effort. It takes a lot of specialists on one hand. It takes a lot of time because sometimes to train some of these algorithms can go into a few days. And after a few days, you may find out it doesn't work. So you need to spend another few days optimizing it and another few days. And it can take a few months by the time your algorithm is anywhere close to being production ready. And even then, the error rate may be, if you're above 80%, or if your error rate is below 20%, you're good. So think of, there is a lot of gaps to be covered there. But the future is bright. The future is definitely bright. So if you were to wake up today and ask Alexa, what's the weather, right from your bed, a bunch of actions happen behind the scenes. First and foremost, what happens is speech to text. Okay? All of the NLU is essentially based on textual data. So the first step that happens is your speech gets converted to text. And while I won't go into any detail on speech to text, remember speech to text is also a machine learning based algorithm. So sometimes if Alexa couldn't process it, or if there were problems with the models that drive the speech to text conversion, you wouldn't get the desired outcome. So that's the first step. The second step, all of the purple boxes are what's under the umbrella of natural language understanding. Okay, so the second step is cleansing. What happens sometimes is you do need to run a spell checker. You need to censor profanity. You do something called as word splitting, right? Sometimes if people type, they forget to hit a space bar between words, right? So you again have machine learning algorithms that know how to split words. The next thing that happens is it goes into a process called as named entity extraction. A named entity extraction is basically taking a very simple sentence and extracting data facets out of it. Okay, an example when you said what's the weather today, a couple of entities that could have been extracted is the place is Toronto without even having to ask for it. And the second one is the date. Okay, and how many of you here are computer programmers? Anyone? Okay, So I'm going to give you a quick example of how you would write something like a named entity extractor in the machine learning world versus traditional programming. So in a traditional programming world, okay, today, for example, would have been a regular expression, correct? You would have extracted it as a regular expression. In the machine learning world, that's not how you do it, because that's cheating, right? You're not using machine learning. What you'll end up doing is you'll have about a few tens to, let's say, a few hundreds of examples, where you'll have different facets of timing. So I'll say today is a great day, tomorrow is going to be wonderful. I was late today. Today turned out to be good, right? I can just go on and keep generating different sentences. And I'll have facets like today, tomorrow, the day after, yesterday, so on and so forth. And what happens is I'll feed all of these to an algorithm, and I'll basically tell the algorithm in all of these sentences, today, tomorrow, the day after, yesterday, are all named entities representing time, okay? And then the algorithm learns that automatically through those few hundreds to thousands of examples. You do not write code to extract that out of it. So what the algorithm ends up learning is a grammatical arrangement for how time is referred to in an English sentence. And that model can be different when you do it for French, will be different when you do it for Spanish, so on and so forth, because every language has its own nuances and grammar. The next step is sentence detection. Sometimes people can ramble, don't even pause. There's no voice modulation. It confuses humans, it confuses machines as well. So machines have another machine learning algorithm that detects sentences, okay? So again, you typically will take a paragraph which is basically rambling words, right? And you'll demarcate saying, here is a sentence, here is a sentence, here is a sentence. And then the algorithm learns to identify sentences, okay? You then have something called as parts of speech tagging, which we saw earlier, right? That's a step where you start rendering structure to your sentence. The next step is something called as lemmatization. And lemmatization is a concept of linguistics, okay? Lemmatization is the process of normalizing words. So for example, if you look at I, are, is, these are all forms of being, right? So lemmatization is, again, it normalizes words to their base form in a way that you can now interpret it in a more consistent way. So you don't basically have 100 ways of saying the same thing, you normalize it to its base form, okay? It's a linguistic concept. And then of course comes the intent detection, which is now the machine can finally infer what is the user asking about. In this case, it's about the weather. And there can be, in a real life situation, you have a few thousands of such intents, and these intents keep going up each and every day. Okay, so intent is basically just like we do all of this in split seconds, and we do it so instinctively, we don't even realize it, that we do it, right? But a lot of machine learning is essentially mimicking human behavior step by step, because machines need structure. The next step is where different implementations vary. So, okay, so while that shows up, so all of what we saw in the purple boxes are fairly consistent. You go into any natural language understanding technology stack, and you'll see all of those piece components in some shape or form. The next step is where different companies have their own secret sauce. Like we at Wisdom have our own secret sauce. Amazon may be doing it a certain way on Alexa. Google will be doing it a certain way on their side. You wouldn't know those, right? But usually what happens invariably is you either end up doing a search, let's say on Wikipedia data, on some data that you've curated or some database of information that you've built yourself. You'll end up creating something called a semantic vector. Semantic vector is basically a machine representation of what you just spoke, but as numbers. Okay, remember machines need structure and machines deal with numbers. Machines don't understand words. A machine won't know what is the meaning of weather. Okay, so at the end of the day, everything filters down into numbers that you're basically then crunching numbers into. You then in some cases, you may hand it off to skills. Skills are specialized scripts that will go perform whatever they're asked to perform. Okay, and finally, you'll have speech to text. And speech to text again uses machine learning. Okay, so like you see, there are many, many moving parts. And eventually, what happens is Alexa comes back and tells you, today in Toronto it's 2 degrees and rainy with partly cloudy skies. I hope this gave you some good insights as to what's happening behind the scenes. And if Alexa were to tell you that she didn't understand what you said, at least now you know it's not just your accent. Thank you.